Okay, off we go. So last time, here's what we were doing. We were looking at boundary flux as a quantity of interest, and we made this observation based on this picture in this discussion that boundary flux accumulates. We have found another accumulating quantity, and again, accumulating quantities are super cool. It's so much neat things that you can do. And just as a quick reminder, let me remind you that whenever you have an accumulating quantity, namely if the whole is the sum of the parts, that alone, the fact that you have a quantity where the whole is the sum of the parts means you can think of it as a kind of a stuff. I'm not saying it is a stuff. I'm not saying physically it's stuff, but it acts like it is. So you can pretend that it is, and you won't be led astray. Right? So we get to pretend that this is a physical stuff. When you have physical stuff, you can talk about the associated density. I mean, that's how stuff works, right? Stuff distributed over volume. You can talk about stuff per unit volume. And when you have that notion of density, then you can make, again, what I like to call an accumulation theorem, where the whole is the sum of the parts, and then on each piece, stuff is stuff per unit volume times volume. Right, so old ideas. We've applied this in a couple of different circumstances already, and now again, as we at the very end of last class, we did the same thing, and I'm just going to kind of wave my hands at this, but we've established that boundary flux is an accumulating quantity. So all that stuff that we were just talking about comes along for free. Now you can draw pictures and try to visualize, for example, how flux behaves like stuff, but you don't have to. It's an accumulating quantity. We already know that it behaves like stuff distributed through the interior. We can talk about the associated density. Now, these details right here are new, right? But we already knew that it was going to have a density that was going to behave like mass density. That was old news. I mean, it has to. It's an accumulating quantity, so of course it does. So all we had to do is establish the particulars, namely, what are we going to call it? What notations are we going to use? Right? How do I compute it? And just as a reminder, when we say flux density, we literally mean the stuff of the accumulating quantity called flux per unit size that it's distributed over, namely volume. So that's just the kind of the details. And again, already we knew that it was going to behave like stuff, and that the whole was the sum of the parts, and it's distributed over the interior. That immediately follows from it being an accumulating quantity. The interpretation of divergence as telling you, how much of the whole is happening in the vicinity of a given point in the interior. That's because it's stuff. All that's old. So this is just how you write down the theorem that automatically results from knowing it's an accumulating quantity. Actually, I'm going to do it like this. I'm going to say we already knew accumulating quantities have the feature that the whole is the sum of the parts. That's by definition in some sense. And we already had established this notion of a density. So the fact that we can compute flux with a triple integral of divergence kind of is the immediate consequence of it being an accumulating quantity. So what comes off as new is that when you interpret flux itself as an integral, namely a vector surface integral, then you get this at least visually new result, Gauss's divergence theorem, that flux integrals can be computed with triple integrals. Everybody on board? Let's see, but this so we were talking about all this stuff last time. Okay, where we left off last time was the very important observation that a lot of students so often will not pay heed to and then step on the resulting landmine, that this has to be a boundary. strictly so, right? It can't just be the border surface. It's got to be boundary in the full sense of the word, including the orientation. In other words, right? The orientation is very, very important. It's part of the deal. Or let's look back at this picture here. Orientations are how this cancellation happened in the first place, right? The fact that we got this canceling with that on this shared face happened because we were following this strict rule about orientations. So our result only, very importantly, only works if our surface here is a boundary. And so looking at this first example, and this is where we left off last time, we started looking at this example, and we're like, hey, okay, well, we want to compute the flux over a surface. That surface is described like so. It is this, that right there with this orientation as given. See, it says inward oriented, and is that a boundary? No, it's not. It doesn't follow the rules. The very strict rules that were necessary to make this all come together in the first place. It just doesn't work. So you cannot apply the theorem to this surface as stated. What you can do, and I believe this is, I think we might have even in a rush said this yesterday, you can talk about this other surface. Exact same underlying surface, but oriented the opposite direction. S minus. That is a boundary. Straight up, no problem. That is literally the boundary of that solid ball. Definition of orientation and all. So, okay. Well, with that in mind then, what we're going to do is we're going to actually, and I'm going to redraw this so I can get everything onto the screen here. I'm going to do like that, and then I want to emphasize that the actual surface we're interested in is inward. The surface that we're given relates to this other surface by being the opposite orientation and thus giving us this minus sign. Right? The blue surface, being as that blue surface is a boundary, I can apply the divergence theorem, and the divergence theorem is what tells me that that flux integral is computed by that triple integral over the ball. Is that cool? Everybody see what happened there? There's a bunch of big ideas all in play in this one. Arguably it's kind of just a don't forget to stick in a minus sign. But I think it's important to recognize the non-trivial ideas. Orientation and inward being the opposite of outward, and recognizing which one makes it a boundary and which one doesn't. Those are sophisticated ideas. Substantial, sophisticated ideas, right? So that's I wanted to make sure that that's fleshed out, and then also then where we use the theorem, and there's just a lot of things that have to be kind of thought through carefully here. Don't forget, of course, this minus sign as algebra requires comes along. Don't just put it in there as a window dressing, perfunctorily, and then drop it for no apparent reason, right? It's part of the result. It's got to come along. Okay. So it's I'm going to say all over, but the shouting, the deep ideas we've covered here. But real quick, how do we proceed? Well, we've got to compute the divergence. The divergence is computed by way of a formula applied to this vector field here, right? So when you take the x partial of the first coordinate, the y partial of the second coordinate, etc., it works out real nice. Just 3 plus x. That's kind of sweet. This example, of course, I crafted to be awesome, right? Making a sale here. Right? So this is not promising it'll always work out this nicely, but it does work out really nicely in this case, and surprisingly often, actually. Okay. Now, and then there's one other little detail I want to point out. How do you compute this integral? And you could do that in rectangular coordinates, but there would be square roots everywhere. It would be a nightmare of ugliness. You could do it in spherical coordinates. That would be a different kind of nightmare. That'd be a trig nightmare. But not even all that bad, probably. I think spherical coordinates would be pretty doable. No big deal, but still kind of tedious. The slick move I want to point out here is that you can break that up as a sum of two separate integrals, and even though this original integral doesn't qualify for any awesome theorems, both of these theorems on the right do. This is a constant over a volume, and boom, right? Constant times volume. Awesome theorem about integrals of constants. And this integral over here, 0 by symmetry. And you will notice I've conspicuously left out the details. And I also did not indicate which line or plane I'm making my symmetry argument through. I want y'all to think that through, right? It's a good little exercise. Do remember on exams you have to tell me what the line or plane is by which you're making a symmetry argument. The word symmetry needs to be in there so I know you're making a symmetry argument, right? And you have to actually, run it into the end zone. You do have to declare that your answer is, in fact, therefore 0, right? So equals 0 by symmetry through whatever plane you're using is a full credit argument if it works, if it's valid, if there actually is such a symmetry argument. So always think through the details of that. And so I want, in particular, don't forget to think this one through. Okay, so much easier to break it up as two separate integrals than to use spherical coordinates or other things. It would be hard. Okay, how are we doing on this example? Everybody happy? Okay, let's talk about some physical examples. There are a lot of physical examples, in fact. This is one of the most powerfully applicable theorems to physics and engineering in really wonderful ways. So I'm going to start with it's kind of increasingly my favorite example, and that is to think about a light bulb. And a light bulb, of course, is typically there's a hot spot. That's where the actual light source is these days, probably an LED, right? Teeny tiny itty bitty little thing that puts out a lot of light, even though there is a bulb around it that's large. Right, the actual source of light is quite small. It's like 1 or 2 millimeters, little teeny tiny. Okay, so here's the thing: light bulbs, they generate photons that come shooting out of the LED, and check it out. They kind of behave like a fluid, don't they? It's a little bit weird. Weird to think of light as being a fluid. It's not wet, right? I'm not saying it's a liquid. I'm saying it's a fluid. It behaves kind of like a fluid does. Anyway, we've talked about this before back in Chapter 3. So it is a weird kind of a fluid. This is worth noting. It is a fluid that is being generated continually. Right, a lot of fluids aren't like that. Like if you think about the air in this room and the air, to whatever extent the air is moving around in here, very little, thankfully, but a little bit, right, a little bit of airflow. It's not because somewhere air is being created. We're not generating air in this room. Air is just moving, right? So this fluid is being continually generated by the bulb. The other thing that's worth noting is that the fluid density is fixed in a steady state situation. So like right here in this room, again, there's light bulbs everywhere. There's light bouncing off the screen. There's light bouncing around all over the place. But as long as we don't move, right, and the light bulbs stay on and the projector stays on, the photons wherever you might happen to look, it's a steady state situation. If the photons are flowing this way, then yeah, they're going to keep flowing that way in a steady state. So the density of the fluid is fixed. That's another thing that's kind of weird about fluids. Think about an animal migration. It's not like that. If there's an animal migration, here comes a bunch of fluid. There were no wildebeests here. Now they're coming at me. Oh, now I'm surrounded by wildebeests, right? So the wildebeest density, the density of the wildebeest fluid, not constant, right? So another sort of a peculiarity of this kind of a fluid. Anyway, in this context, given how this particular fluid works, we can make natural interpretations of divergence. And so let's entertain real quick. What if I were looking at a little region right there, and I want to think about the flux through that little sphere, let's say oriented outward, the usual way. Yeah. What's the flux of the fluid through that little sphere? And I claim it's 0. I claim it's naturally, dare I say, obviously 0 in a steady state situation. Let's think through why that is. Roughly the point here is that every photon that flows in also flows out. Right? So there's a perfect balancing correspondence. And to whatever extent you have inward flow kind of on the side closest to the bulb, you also have a corresponding outward flow on the back side, the dark side, you might say, of that little sphere. Right? Every photon goes in and out. So it all cancels. So, all right, let's think about what the consequence of that is. Given that the fluid that flows in is always balanced by the fluid that flows out on that little region, if there's no boundary flux, then there's no boundary flux density either. There's no flux there, so no flux density there. Does that make sense? Now, by contrast, let's think about an analogous question around the sort of the right at where the bulb is. Let's think about that little volume, again oriented outward, just because. How much flux is there through that little sphere? A lot. Right? I mean, you think about it, we have a light bulb right there. That light bulb is shooting out a lot of photons. All of the photons that are being created by this light bulb, they're all coming out of that same LED. So all of the photons, all 100 watts or whatever it is, right? All 1,200 lumens of photons, they're all flowing through that blue sphere. A lot of flux. And if you think about it, the volume is small, right? That little blue sphere, I could make that all fairly small. I could make it as small, as long as it still contains the little LED at the middle, I can make that quite small. So altogether at that point, I think it's fair to say flux per unit volume, well, we have a significant amount of flux distributed over a teeny tiny itty bitty little volume, and large divided by small is huge. Yeah? So, in fact, all of this will track. If you can write down the formula for the vector field that's created by this light bulb, you would find that as drawn here in this picture, the divergence would be huge at the middle, and it would be 0 everywhere else. No bulb, no flux, no flux density. Is that satisfying? Okay. All right. Okay, one of my favorite things about this example, there's actually a couple things I like about this example. For one thing, we can visualize the whole story, right? I think we're all pretty comfortable with the idea of a light bulb. Everybody knows what light bulbs aren't a mysterious concept. It's nothing unimaginable or abstract, right? It's light bulbs. There's one, right? It's completely relatable. And we're also pretty comfortable with the idea that light creates a flow of particles that it's a little bit weird to think of it as a fluid, but it behaves like anyway. It's not a huge stretch. We're comfortable with there are these little particles shooting out of it. Very relatable. The other thing I really like about this example is because of that relatability, we get a viscerally satisfying example of a claim, this abstract, creepy claim that I've made in the past, which is that flux that we detect on the boundary actually happens in the interior, right? I've said, okay, even though we detect it on the boundary, that's not where this fluid flow is coming from. It's not coming from the boundary. Light's not coming out of the boundary there. Where's the light coming from? It's coming from the interior. Well, of course it is. That's how light bulbs work. Right? So, completely relatable that flux may be measured on the boundary, but it's actually coming from the interior. And furthermore, the divergence is telling you exactly where in this great big interior the light's coming from. It's coming from where the divergence is huge, and the divergence is huge at where the LED is. Everybody seeing that? So if you want to get comfortable with this creepy sort of seemingly abstract idea of detected on the boundary but coming from the interior, this is your example. This is, I mean, it literally is coming from the interior, even though it's measured on the boundary. So I think that's a nice aspect of this as well. Okay. All right. Let's look at this next example. Different kind of fluid. Importantly, different fluid. Here we have a gas. And I'm imagining a scenario. By the way, this is a gas that's like out in outer space. Imagine that this is like a nebula. Something like that. Just a cloud of gas sitting out there with no other mass anywhere around. No gravitational influence from nearby stars or anything like that. It's just a cloud of gas in space, nothing else. Well, gas, again, not created or destroyed. Right? Light gets created, not gas. So this is a very different kind of a fluid. Right? Also, gas, if there is a flow of gas, like imagine what's about to happen here, the gas starts expanding, maybe because the temperature starts rising and the gas starts to expand and it's taking up bigger and bigger space. The density is not even close to constant. As a finite amount of gas expands, well, it's a finite amount of gas. And so looking anywhere in the inside, the amount of gas in any given little small region is decreasing because the gas as a whole, same amount of gas over bigger and bigger volume, constant divided by increasing, means the density is decreasing. So again, not like light in that sense either. Right? Very different sort of physical rules of this kind of a fluid. So I am going to assert, and we'll get a kind of a confirmation, kind of a check anyway, that the flow, when you have an expanding gas, again, perhaps because the temperature is increasing or whatever, if the gas is expanding, I claim that the vector field that describes the flow is this formula right here. Something to that effect, anyway. So now, how do we interpret that? Well, a couple of things we can interpret from this. On the one hand, as that gas expands, I can think about the amount of flux, right? And you can see it happening right there. You can see our fluid is flowing out of our surface. So there is a flux. Fluid is passing through the surface. And again, just a quick reminder, what that represents, if fluid is passing through this boundary surface, that means that over time the amount of fluid remaining on the inside is decreasing. So the density is decreasing as this flux is happening. And now I'm going to write down the divergence theorem. Here's Gauss's divergence theorem, and I can compute for this vector field, I can compute what the divergence is. The divergence of that vector field is just a little bit of algebra. It's 3k. By the way, you want to check me on that. Make sure that you understand where that 3k comes from. It comes right out of taking this vector field and writing it in coordinates, applying the formula for divergence. 3k will be your answer. Again, by the way, as always, just a reminder, whenever I say check this up for yourself, the implicit subtext is, and if you get stuck, come talk to me in office hours. I'm happy to help. Right? So how do what's the interpretation that I make then of this, this 3k? What is this, what's this telling me? And I'm claiming that tells you, if the total density is decreasing, this tells you where and how much. So the fact that, at this point, the divergence is 3k, that's a commentary on how fast the density at that point is decreasing. And this point right here, or that point right there, or this point, wherever it might happen to be, right? Whatever point you're looking at, it's always the same amount that the density is decreasing at every point on the inside. And by the way, that it better be, right? Because if you have a gas that's expanding, right, you can't have a situation where there's a higher density over here and a lower density over there. The pressures would equalize that. So it should be sort of a uniform decrease of density, because it's a uniform expansion of the fluid. And that, by the way, is kind of a confirmation, it's a check of reasonableness, that this might actually be the vector field describing the flow in the first place. We've just confirmed that vector field, as it should, suggests a constant decreasing of density uniformly throughout the insides. Again, as it sort of has to be. So, different interpretation, right? I mean, divergence up here in the... Well, let me erase my mess here. Up here, divergence was telling us where the photons are coming from. It's telling us what you might call generation density, per unit volume, how much fluid is being generated in this little space, because that was the nature of the fluid we were looking at. Here we're looking at a fluid of a very different nature, fundamentally different, but not just physically different. It behaves according to different rules. And so we get a different interpretation. Here, divergence doesn't tell us how much fluid is being generated. It tells us how much fluid density is decreasing. So, different kinds of fluid. All right, now, just to let you know, and this is just a hand-waving reference. This is not part of the course. You don't have to know this, but just to kind of foreshadowing, just to put this onto your radar, there are some kinds of fluid where both of these things happen, where there is a generation of fluid, kind of like with the photons coming out of the light bulbs, and furthermore, the density may also be decreasing over time. So, for example, if you were to look at let's say, now this is a weird example, perfectly reasonable. Basically, I'm going to talk about what I'm going to call migrations of animals. We tend to like to think of migrations of animals as being, fairly quick, right? I mean, those birds are flying pretty fast, right? We think of that, we visualize the motion, right? But what if we were to think about sort of, less of a seasonal migration and more of a long-term, decades-long, slow migration of, or you might imagine, like, I don't know if y'all are aware, did y'all know that pythons have invaded Florida? You go to the swamps now in Florida, and it's not just alligators you have to worry about. There's big pythons in there, right? Because somebody brought in a pet python and then realized they had made a huge error, and then was like, I'll throw it in the swamp. right? And so now there's something like 500,000 pythons in Florida.
How did it, like, read if it was...
I don't know. I wasn't there. It might have been maybe somebody had 2 pet pythons. I don't know. You never know. Anyway, so let's talk about, okay, over the years, right? That started off with just a couple of pythons there, right? And then over time, the python fluid, right, slowly expanded over a lot of Florida, as I understand it. I'm not an expert in this area. So there's a couple of things happening there. They literally are generating more pythons. Pythons are being born. That's a generation of the fluid of pythons. But they're also not a constant density situation, right? The python density in certain areas was getting bigger and bigger. Or as the pythons, perhaps maybe they decided, hey, we're going to move south because we like the warmer weather. That there could also be a flow of this fluid, kind of like the movement of a gas. So both can happen at the same time. So if you wanted to understand how do you kind of keep track of this kind of a sort of a dual-featured fluid, I make the observation that when you generate pythons, they either stay, right, which increases their density, or they leave, which creates flux. But one or the other, take your pick, and therefore these two things have to add up to the generation rate. And if you then think about that differentially per unit volume, then what you get is an interpretation of divergence, and then you have to kind of figure out by other context clues which of these or how much of which, and that's a whole separate matter. But anyway, I just wanted to point out that sometimes you have to kind of account for both, depending on the nature of the fluid. All right. Okay, let's talk about gravitational fields. Now, we don't think of gravitational fields as being the flow of a fluid, right? What fluid? If I hold my pen stylus out here like this, gravity's pulling it down, I'm not visualizing there being a fluid of any sort involved in that story. It's just this abstract, physically unmanifested vector field that just kind of magically, fundamentally applies forces. Okay. All right. Well, you can write down the formula for gravitational field. There it is. You may recognize this from Chapter 3. I wrote down this exact vector field. I pointed out that you can rewrite it like so. And this is what we call an inverse square radial vector field. You can see why they call it inverse square, because it's literally inverse square in terms of its magnitude. And you can see why we call it radial, because that unit vector, the direction that this is pointing, is always radial, outward or inward from the point source, right, at the origin. So inverse square radial, yawn. Here's the thing. Unexpected, but true. This formula right here for gravitational fields that I have a kind of a picture of right here, if that picture looks vaguely familiar, indeed that is literally exactly the exact same picture that I have here. In fact, the formula for the flow of a fluid of photons coming out of a light bulb is exactly the same structure. It is inverse square radial. Different constants. Appropriate to this being a different kind of a substance, right? But it's exactly the same structure, underlying mathematical structure. So what that means, and this is crazy thought, wild, outrageous thought, gravity seems to behave exactly as if it was a flow of a fluid of some sort. So maybe it is. I mean, when something is behaving exactly like some other very familiar and relatable phenomenon, it stands to reason to suspect maybe it literally is that same phenomenon. Right? So there is a point of view that you can take on gravitational fields, and conveniently, it doesn't even matter if this is true. Right? Whether this is physically true or not, couldn't care less. But gravity behaves as if it is a bunch of emitted particles created by mass. It's as if every particle of mass is shooting out little particles that kind of behave like photons. But they don't communicate light, they communicate gravity. If that were true, doesn't matter if it is, if it were true, we would get the exact same vector field. So, since it behaves as if it's true, we can get away with treating it like it's true. And I think that is just bonkers useful. It is so useful. Again, whether or not gravitons, by the way, is the name that, by the way, I didn't think of this. This is a long established idea, right? Whether gravitons do or don't exist, ask a physicist and be prepared for a very long conversation to ensue, right? But it doesn't matter. For our purposes, gravity behaves as if they do, so I'm going to pretend that they do, and that will always lead me in exactly right directions. So I'm going to just make reference to gravitons like they're a thing, because they might as well be. So let's, with that in mind, let's look at this equation right here, and what that's saying is that the amount of mass that you have that's creating your gravitational field should be proportional to the amount of flux that you would measure on the boundary. Now let's think through, why might that be, right? More mass, more flux. Why is that? Well, more mass means more gravitons. And when you create a graviton, that graviton has to pass through and therefore create flux through the surface. So more mass means more gravitons means more flux. So this idea of gravitons as being the thing that the gravitational field is representing a flow of, that idea of gravitons immediately connects. In fact, I will tell you what I'm going to do. I'm going to recircle this in orange. The idea of gravitons is what relates mass to gravitational flux in an intuitively, visual satisfaction kind of way. How we doing? Everybody kind of seeing that angle? Okay, well, we're a hop, skip, and a jump from a very powerful interpretation of divergence. So these being the same, okay, fine. Well, let's look at this equation across the top here. Hardly anything happened in this equation. This constant here kind of comes along for the ride. Basically, all we're saying here is mass is an integral of density. Of course it is. That's old news. That's ancient history old news. Right? Now let's look across the bottom. What's going across the bottom? I've just literally recopied Gauss's divergence theorem. Nothing more. That's literally just Gauss's divergence theorem. So that means that these two integrals are always equal. That means that these two integrands have to always be equal, because this is true for every domain. And that then gives us a way to compute the divergence of a gravitational field. That is a really, really powerful idea. Now, it's tempting to say, well, can't I just compute the divergence of this? And the problem is, computing the divergence of that only applies if you have a single geometric point mass, which is not really how the physical world works, is it? Right? Mass is not at geometric points. That's a abstract construction that we make for convenience. So that's not the real world. Also, this assumes you have only a single point of mass. And if you have something much more complicated, in other words, if you have a realistic scenario where there's mass distributed, perhaps with differing densities. Maybe it's got more density the further you get over to this edge, something like that. Okay, well, the density there is very different from the density there. Okay, yeah, fine. You get some crazy vector field describing the gravitational field, but the divergence is straight up just the mass density. End of story. Nice and simple. You don't even have to compute the nightmarish, the horrifying vector field describing the gravitational field from this cloud of mass. I can't. It's just too much. It's too many. There's mass in different locations. Oh my God, it'd be very, very hard to write down the vector field itself, but the divergence is easy. It's just mass density. Oh, very cool. Powerful ideas. All of which we get only because Gauss's divergence theorem allows us to kind of have a foot in the door. Oh, very cool. Okay, alrighty. By the way, this is one of the reasons why physicists like the term flux density. You look at this and it says mass is proportional to flux. You look at this and it says mass density is proportional to flux density. It rolls off the tongue exactly the same way. That literally rolls off the tongue because of choosing to think of this as flux density. Okay, all right, enough of that. Okay, now let's talk about electric fields. Now, electric fields are not relatable, particularly. Light bulbs, we see them every day. Nothing creepy about light bulbs. It's a very common experience. Gravitational fields, not the most abstract thing in the world. We have to walk around all day, every day, dealing with the fact that gravity is pulling us downward. Make sure not to fall down and, stuff like that. And you drop something, it goes to it doesn't fly up into the air, it goes down. Right? So gravitational fields, again, a pretty relatable idea. Electric fields, really not. Electric fields are so unrelatable. Humanity didn't even notice them until, a couple hundred years ago? Right? They're just not very relatable at all. They're very hard to sort of relate to. So, in case you were wondering why I spent all this time talking about gravitational fields, you might be thinking to yourself, I have no intentions of leaving planet Earth. Gravitational fields will always be constant. Gravity's always going to point down. It's always the same. Not much to understand there. Who cares about, if I'm not going to be an astrophysicist, why do I need to know this, right? Well, the reason why is because this is the relatable example that is the perfect analog of electric fields, which you are almost certainly going, as engineers anyway, almost certainly going to be studying in great detail, right? Every contraption, every piece of electronics, batteries, any electric wiring, right? Anything that has electricity in it, there are electric fields that you have to know and understand and have a good intuition for. And the beautiful observation is they too are inverse square radial when coming from a point source. So structurally, electric fields are just like gravitational fields. So thinking of mass as creating a gravitational field represented by a flow of these little particles that may or may not exist. Right? That's the perfect model for thinking about electric fields. Electric fields are fields created by not mass but by charge, right? By electric charges. Charges create fields. Those fields, you can think of them as representing a flow of some little fluid of little teeny tiny little particles, which I don't want to give a name to because you're going to be tempted to call them electrons, and that's not what electrons are, right? But anyway, you can imagine electric fields as kind of representing a flow of little particles, and then if if charge creates these little particles, well, more charge means more particles means more flux, and charge is an integral of charge density, and Gauss's divergence theorem continues to be true, and so we get, again, this powerful result here. And so big ideas about how to think about fluid flows and inverse square radii, all that stuff builds up to pretty good intuition for Maxwell's first equation in differential form. Right? And that is the divergence of an electric field is proportional to the charge density. Actually pretty straight up believable. Thank you, Gauss's divergence theorem, that made that possible. Okay. All right. So I as engineers, I think it's important that y'all see all this, emphatically. And of course, you're gonna take courses if you haven't already in E&M. Right? When you study E&M, this is really useful. Right? And other things that we're going to do later, hopefully later today, also super duper useful. You will see these things in your future courses, but seeing how this connects directly to these big math theorems, I think, is particularly important. Okay, off I go. Next theorem. By the way, a quick reminder, how did we get Gauss's divergence theorem? Well, we got Gauss's divergence theorem by starting off thinking about what the boundary of a solid ought to be, and how specifically do we orient boundaries of solids. Right? Solids have a boundary surface, which are oriented by normal vectors according to certain rules. Right? All of that was the first step in the door that allowed us to observe a particular accumulating quantity. And then it was all downhill from there. Okay, well, guess what's going to happen with Stokes's curl theorem? We're going to consider another type of object. We're going to look at oriented surfaces. So surfaces oriented by a corresponding normal vector. If you have an oriented surface, how can I talk about the boundary curve of that surface? And specifically, which way is it going to be oriented? I need to know whether the curve's orientation is going to be that way or that way, and we've got to decide which. Correction, we have to understand the established standard. Right? Again, it's arbitrary, but it has been highly standardized, and we're stuck. Okay, does everybody, before we get into what that standard is, does everybody see the situation? We have a different kind of now a surface instead of a solid. It has boundary curve instead of boundary surface. And again, we have to decide how to orient. Let me get rid of the confusing picture there. We have to figure out which direction the orientation is. Everybody with me? Okay. So there's a rule. Let's follow the rule. There's different ways to state this rule. I'm going to show you the one that I think is the most user-friendly, the most convenient in practical circumstances such as Math219 exams, right? But also practical circumstances that will come up in engineering. Here's my take on how to do it. You look at your surface. You pick a point on your surface that is near the boundary, not at the boundary, not on the boundary. Very importantly, not on the boundary, but near the boundary, right? And you think about the orientation of the surface at that point, near, not on, near the boundary. And then you use your right hand. That's the standard. It's arbitrary but standard. Right hand. As you know, as we use our right hands for a lot of things in this course, right? You put your thumb in the direction of the surface normal. In this case, it's upward. It could be downward. It could be to the side. It could be that way. Whatever. In this case, upward. Thumb in the direction of that. Now look at the fingers of your right hand and notice they kind of they're sort of pointing around your thumb, suggesting a rotation around your thumb of your right hand. And if I were to do that here for this, that rotation would be kind of around that way. I think you'll see. Everybody see that that's this rotation? So I'm going to say that for that surface normal, this defines this thing I like to call a swirl. And the swirl, geometric appeal here, if you were to imagine how that swirl, how does that kind of meet up against the boundary, here again, by the way, is our boundary curve. How does that swirl, I say side swipe, which direction along that boundary does this swirl kind of push, you might say? Right? Well, it's pushing that way in this case. And that's the standard for how we determine boundary orientations on boundary curves for oriented surfaces. What do you think? Anybody see how this works? What's nice about this rule, by the way, is it's a lot easier to move your hand than to move your eyes. I was here just so you know. I mean, here's another take. Another take is that when you're up at sitting, if you were sitting at the top of the arrow representing your surface normal, then when you look down, the orientation is the one that would be going, that would appear to be going counterclockwise around the sort of the axis of the surface orientation. And the problem with that is, while it is easy in this case to imagine looking down on a surface, what if the normal vector were going the other way? What if we had a circumstance where the normal vector were downward, and now you'd have to imagine yourself being down here and looking up, and so you're going to be, this is ridiculous, right? You'll be taking your test, and you're like, okay, so my surface is, okay, so I'm like this, and I'm like that, okay, but that, as seen from how I will draw it, is like, you got this weird kind of perspective games you find yourself playing, and I think it's a lot easier just to be like, oh, so the orientation's down, you just put your thumb down, and now just look right at your fingers. I just think it's easier. In practice, student-friendly, I think this is the best one. Okay, sounds like everybody's good with this. Okay, with that in mind, good news. We have a new accumulating quantity. Gotta love it when this happens. The accumulating quantity is circulation around surface boundaries. So boundary circulation. By the way, where have we heard that before? Green's theorem. Green's theorem is about the accumulation of boundary circulation, isn't it? It's just over a two-dimensional region in the plane. Now we're looking at a two-dimensional surface sitting up in space, right? So different geometric context a little bit, right? But it's still a two-dimensional thing with a one-dimensional boundary curve around which we can talk about boundary circulation. And boundary circulation accumulates, and for morally the same reason, because if you look at that part of the boundary of S1, oriented as it is supposed to be, and then you look at this part of the boundary circulation around S2, also oriented the way that it's supposed to be, right? Those shared edges, those terms on the same shared edge have opposite orientations. Same shared edge, opposite orientations, and so they cancel. It's morally the exact same argument that we gave when we were doing Green's theorem. And I think it's a really healthy exercise to think that through. Right? In fact, let's do this. Let's retain this picture here, and then let's look at this picture that we saw when we were doing the other theorem. And again, that direction on that piece, that direction on that piece, and they same shared edge, opposite orientations, they cancel. It's the same exact argument, just in a slightly different context, floating up in space instead of confined inside of R2. Cool. Okay, so, again, we were kind of done. We have an accumulating quantity. Accumulating quantities behave like stuff. Stuff has a corresponding density. Density can be integrated to compute total amounts. And look, this is a picture you can look at if you like, if you want to have some, sort of geometric sense, but we've already established that when you have accumulating quantities, their stuff, they have a density, there's an integral theorem. So these are just particulars if you're interested, but here's the theorem right here. Circulation accumulates, old news. Densities allow us to write stuff per unit in this case, stuff per unit area. The one little detail that we do have to insert there is what is the corresponding density, circulation density. How much circulation is there per unit area? How do you compute that? And the answer is it's this thing right here. It's curl dot normal vector. So that's the formula and the name and the interpretation. Curl dot n. So you'll notice that is what I have in here as my density. And so we have our first take then on Stokes's curl theorem. Stokes's curl theorem says circulations are computed by that integral right there. Let me pause before there's one last little thought to connect there. But everybody see how this is morally the same as Green's theorem. It's about circulation as an accumulating quantity computed in relation to its corresponding density. Okay. All right, so the last real quick little observation is to say, hey, look at that right there. How about that? In ds. That's literally our ds vector. So a little bit of a rephrase, and I think this is kind of a nice rephrase and this is what I like to call Stokes's curl theorem, and that is circulation. Boundary circulation is computed as a flux, vector surface integral flux of the curl. Everybody happy? All right. Let's see here. Yeah. Okay, all good. So, let's see an example. Again, just from a computational point of view. Here's the statement of the question. I do want to point out real quick, I know I say this a lot, but don't think of this course as being about methods that you apply. Think of this as being about tools that if you understand the tools, you can associate naturally to problems as they arise. You can pick the right tool out of your toolbox and apply it as needed, right? So this question here does not announce itself as being a Stokes's theorem question. It just says compute this line integral. And we have various different methods for how to compute line integrals. It doesn't say Stokes's theorem anywhere in the statement. You could, in fact, even kind of feel like the statement of the question is pushing you towards using this parameterization. And that was our first formula for how to compute line integrals. We parameterize, we pull back through the parameterization, right? You compute the x prime, and then dx is x prime dt. You pull back, right? Just like in chapter 6. So, just a reminder, always head on a swivel. Don't just do it the way that first occurs to you, right? Think about your options. Entertain the possibility of maybe using a different tool. And sometimes those different tools are a lot easier. You can probably see this coming, by the way. This would be a nightmare if you were to use the parameterization. Just be an absolute nightmare. That might be a little bit of an overstatement, but keep in mind, there's a formula for x. So that is going to get squared and show up there as well. That is going to get exponentiated. I'm already thinking this looks like a weird integral. It's doable, but it's not nice. So again, don't just follow whatever your first instinct is. Think about your tools and consider how you might use more powerful tools. Okay, so here's how we're going to use the more powerful tool. We've got to look at our curve. We have this curve C. It's parameterized like so, which I claim goes around this unit circle in the XY plane clockwise. There's quite a bit to think about there. Roughly speaking, this minus sign is why it's going clockwise instead of counterclockwise. And so think about, how you would normally parameterize this and how you might view that as being sort of reflected over one of these axes and what would be the consequence in the parameterization. And make sure you're comfortable that this is, in fact, what our curve is. Again, come to office hours if you're not sure how to make that interpretation, but make sure that you're comfortable with that. Okay, and now the big question. Coming back up to Stokes' theorem. Again, all of these big theorems, all of these accumulation theorems, they all come with a catch. The catch here, just like with Gauss's theorem, that's got to be a boundary. This is non-negotiable. Doesn't make any sense to apply a theorem that requires it to be a boundary to something that isn't a boundary. It just does not work. It's not okay. It's 100% garbage. Makes no sense. So you gotta make sure that if you're going to use this theorem to compute a line integral, gotta make sure that your curve is a boundary. So looking at our picture here, is this curve a boundary of something? And in fact, it is. You might have been expecting me to say no, but in fact, this one is. It's fine. It's not a problem at all. This is straight up the boundary of this surface oriented, as I have it drawn here, downward. And another nice little exercise. Think about how, okay, we've got this surface S. How do we, I can see the geometry is that the curve is literally the boundary of the disk. That part's fine. But how do I know that the boundary orientation is what it's supposed to be? We play the usual game. Right hand, thumb, in the direction of the surface normal, right? There's our surface normal. It's down. So I've got to take my right hand, I've got to point my thumb down. That's the direction of the surface normal. Now, with my thumb down, look at the fingers of your right hand. And notice, because my thumb is pointing down, my fingers are kind of pointing clockwise around. So that makes a swirl. Oh, it's going to be hard to draw a little bit, but the swirl is kind of like that, if you will. And does that swirl sideswipe the boundary in the direction that I've indicated? Why, yes, it does. Everybody good? Okay. How did I know to try downward in the first place? Who'd have thunk it, right? Wouldn't you have? Most people's natural instinct is to think, okay, well, how about this? I'm gonna make it upward. We'll come back to that in a minute. I'm going to set my normal vector as upward, I would think. I don't know. Why not do that? Why didn't I do that? Well, in fact, one could make the case that maybe you kind of should entertain that possibility and then play the game. And it's an easy game to play. Well, if it were oriented upward, fingers would be going counterclockwise, which is wrong. It just doesn't work. So this is a trial and error kind of a situation. When you're trying to reverse engineer the orientation for the surface, whose boundary is the curve, thankfully there are only two options to have to entertain. Try them both. See which one works. One will work. One will not. Does that make sense? Okay, so no problem. This is a boundary. And again, this curve being a boundary, boundaries, I can apply Stokes's curl theorem. There it is. Let's see here. Come to think of it, I am going to need to shrink. Here we go. Stokes's curl theorem. I can compute circulation as a flux of curl. Then I have to compute the curl. By the way, just to be clear, so this is our new surface oriented like so. I can compute the curl itself. The curl itself is just plug and chug from the vector field. Right, take that vector field, plug it into that curl formula. Again, flashback to chapter 3. Make sure you know that formula, right? There's formulas you just have to know. Make sure you know the formula for curl. Punches up real nice. Again, I crafted this example with sails in mind, right? I'm trying to make a sail here. I'm trying to persuade you that this is awesome, so I picked one where it works out awesome, and that curl vector sure is nice. Now, then we kind of have to return to the picture, and don't forget that there is this normal vector right there, right? We've already agreed that the normal vector is not only downward, but straight downward. Geometry of the picture, right? The surface is clearly perfectly horizontal, so the downward orientation is literally straight down, which means that normal vector is 0, 0, -1, and it's all over but the shouting. Because our integrand is -2, that's over this disk, whose area is obvious and easy integral, nothing to it. What do you think? Everybody good? Okay. Alrighty. Okay, so now this next thing is a little weird. This is non-critical. I'm going to do my best to not spend a lot of time on this, but I think it's really useful for visualizing and geometric intuition. I'm a huge fan, but this is about intuition and comprehension. There's not any particular computation in this little discussion here. But anyway, so flashback to the fundamental theorem of line integrals. Right, old news. We wrote this down. Then we observed that TDS is dx. And then I made this observation that, well, this is the very simple idea of change density. It's literally change per unit length along the curve. That's the name, change density, right? Again, it's an immediate result from interpreting kind of sort of directional derivatives from a chapter 2 standpoint. This is all stuff we talked about back in chapter 6. But then the question arises, okay, well, yeah, but how do I think about not gradient dot t, but just gradient by itself? How do you think about that? And I made the following suggestion. It seems a little weird, I know, but if you think of this as not stuff per unit size, but stuff per in the sense that there's a multiplication here, but kind of per what I'm going to call oriented size, if you will, dx. Dx is telling you not only how big your piece of curve is, but also which direction is that piece of curve pointing, what is the orientation on that piece of curve, right? That's both of those, right? Dx is literally orientation and size together. So if you will interpret dx as being oriented size, then doesn't it make sense, I think, that this being the thing that you dot with oriented size to get stuff, I think it makes sense to call this an oriented density, in a way. just being flexible about the notion of a density. Instead of stuff per unit size, it's kind of stuff per unit oriented size. Anyway, that's the idea. Whether you like it or not, this is a take that you can view this formula by, even if you don't like to view the formula in this way. So with that being said, erasing the distracting stuff, gradient is sometimes called oriented change density. And it's actually very, very natural. It's very communicative of exactly what it is. The gradient is an oriented thing that's telling you about how much the function's changing in a way that relates to dx, whose, among other things, tells you the size of the little piece that you're moving over. So it kind of makes sense in a natural way. And furthermore, look at this. You can see in known established interpretations of the gradient, check it out, its magnitude is literally telling you how much the function's changing in sort of the maximal direction. In other words, independent of which direction you're moving on a mountaintop, right? If you're hiking on a mountain, not the top, but if you're hiking on a mountain, the question comes up, how steep is the mountain? Independent of your trail that you're walking along, how steep is the mountain? Yeah, it's the magnitude of the gradient. Which direction is uphill on the mountain? Well, that's the direction of the gradient. Right? So this, viewing the gradient itself as being an oriented thing that's telling you how steep the mountain is, it's actually really natural. So with that point of view in mind, I'm going to now do, in fact, we've already done the same observations from the point of view of now Stokes' theorem. So again, we wrote this down previously. That's Stokes' theorem. We rewrote that as that previously. Again, old news. We already knew, we already observed that that's equal to that. And now again, I can say, well, circulation, I'm viewing it as a product now, again, in kind of this familiar way. It's just that now, instead of size alone, I'm thinking of circulation per unit oriented size. Again, that's what the ds vector is. ds tells you the orientation and the size of your little piece of surface. And as such, it just makes loads of sense to think of curl as being an oriented circulation density. Again, circulation, because that's the accumulating quantity in question, and oriented because, let's see here real quick, let me circle to get the colors straight. Oriented because it's pointing in a direction. It's pointing in a direction that is telling you in some sense what is the direction that this circulation is happening around. And its magnitude, I claim, is telling you in some sense how much circulation is happening in general, as opposed to around whatever axis you might be interested in. So this is a really powerful resulting interpretation that comes directly, let me get rid of my distractions here, this comes directly out of thinking of curl as oriented circulation density. And it's it's a lot to digest, I know, right? But that point of view, in comparison to this perfectly analogous point of view up here about gradient, right, gives these really powerful interpretations. So that, just to summarize here then, and this is literally just summarizing what we stated here, the curl vector has a direction, it has a magnitude. The direction is telling you about the axis that the rotation of the fluid is happening around. And the magnitude is telling you, in some sense, how powerful is this tornado? Right? It's telling you some sort of a measure of the strength of the rotation of the fluid around the axis indicated by the direction that the curl points. Everybody buying it? So that's nice. The last thing I'll do just real quick. Oh, no, I only have 10 seconds. I don't think I can do this in 10 seconds. Okay, all right. We have to draw the line right here. I'm going to have one last little comment here about just sort of a case in point. But anyway, this is a natural starting point for next time. Okay, see y'all later. Have a good one.